Welcome to Brain Vision.
A 67-kilogram person ingests 0.35 curies of tritium. We're told to assume that the tritium spreads uniformly throughout the body, and that each decay corresponds to an absorption of 5 kiloelectron-volts of energy. We're given the half-life of tritium, and electrons is 1, and the first thing we need to do is calculate the absorbed dose in rad and the equivalent dose in REM over a week. So we know that initially, the activity is 0.35 curies, or equivalently 1.295 times 10 to the 10 decays per second. Decays per second. Now we can calculate the decay constant by taking the natural log of 2 and dividing by the half-life, which is given. This comes out to a value of 0.1788 times 10 to the minus 8 inverse seconds. So, and not the total number that we start with, the total number of tritium atoms that we start with, is given by A, the activity, over lambda, the decay constant, and this works out to be 7.2427 times 10 to the 18. So this is the number of tritiums that we have. So the first thing we want to do now is to calculate how much has decayed after 1 week. So we know that the total remaining must be equal to the total that we start with times the exponential of minus the decay constant times the amount of time that has passed. So plugging in t equals 1 week and being careful with our units, we find that n equals 0.9989 and naught, which means equivalently that 0.0011 times n naught of tritium has decayed. So this is the number of decays over the course of 1 week. So now to calculate the dose that is given over the course of 1 week, using the fact that each decay imparts 5 kiloelectron-volts of energy, the dose is 5 keV times the number of decayed tritium atoms, 0.0011 and naught, 0.0011 and naught. We take this and divide it by the mass of the person, which is 67 kilograms. And this is the dose absorbed over the course of the whole body. And this works out to be 0.0951 joules per kilogram, or equivalently 9.51 rads. And that's our answer.